This meeting is being recorded.
Okay, so I will start with this introduction video. Okay, now the introduction video is the kind of the most basic video, and it's kind of important because I know that there are many people coming from different different areas. Sorry, just one second. Let me just try to do something else. Just let me make it bigger. Give me a minute. Yeah. So can you see my screen?
Yes, sir, it is visible.
Yes, sir. Yeah.
Okay, good. So, yeah. So I'm sure many of you are coming from CS background. So some of you have already seen algorithms in some sense, formally. Some of you have come from something other than the CS background, but you have still done a little bit of courses in algorithms. And some of you don't have anything, you have not gone over any particular topics in algorithms. So this video is something very crucial because the concept of algorithms depends upon the person that you ask. Okay, so I'll explain you very quickly soon. Okay, so what is an algorithm? So algorithm is nothing but a step-by-step process of doing a particular task. Okay, now this is a very generic definition, and you have done the first algorithm way before in your childhood. So when you have added two numbers in whatever ways you had done it, that was an algorithm. Your parents had taught you to use your fingers in a particular way so that you can count or add numbers. That's an algorithm. In fact, when we came to such complicated numbers like say 53 and 49 or even higher numbers, we were taught a particular way of doing it, right? You get the units, match the unit places, 3 and 9. 3 and 9 is 12. You put 2 down and take 1 up, 1 on the top, and then add 1 plus 5 plus 4. You kind of memorized that step-by-step thing and have done it. Now, I'm not going over this step-by-step thing. You all know that. Now, question is that why was it done? There are two important parts to this whole thing. Why did your parents teach you to add 53 and 49 like that? And more importantly, does that process of doing it give you the correct answer? Does it give you the correct answer always? So the first thing is that whether the algorithm gave you the correct answer or not, that I don't think many of you actually thought about it ever in your life. And the second thing is that you kind of assume that in this thing that, of course, I mean, if I was taught, it must have been giving me the correct answer. So great. The second thing is that you was taught to add 53 and 49 like that so that you can save time, save space. Earlier days, much before when people were hunter-gatherers and all, people used to count it by counting pebbles. You have 53 pebbles, you have 49 pebbles, then you take them together and you count how many of them are there altogether. That's also a valid way of counting, but it's a slow process. it also requires a lot of other objects, like lots of pebbles, right? So algorithm, so this is also an algorithm. Nobody says that just counting 53 plus 49 using pebbles is not an algorithm. It is an algorithm. So is 53 plus 49 in the way that you have been taught. So then, there any of this step, any of this process of doing things step by step is an algorithm. Now, one algorithm is better than the other because it helps us to do it faster or use less resources or less space and so on. Now, what happens if I ask you a much more simple question, that which number is bigger, x or y? Here are two numbers, x or y. What will you do? Now, I know that you guys are very smart and you can just see it and do it. But what happens if I tell you this algorithm? Right? So this is an algorithm that does it, right? Check it from the left to right. And as soon as you first see the first digit where they differ, whichever is larger, you can output by doing that. Again, this is a valid algorithm. This is an algorithm that gives you some answer. But here is another algorithm. Now you check the first 5 digits from left to right. Now, if you find there is a mismatch, then output that. But if the first 5 digits are same, then output x. Now, see, this is another algorithm. Which algorithm is correct? Can anybody say that?
First one.
The first one is correct.
Sir, I think no.
Yeah.
Sir, the first one doesn't count the number of digits.
Doesn't count the number of digits. No.
Also,
So for the first one, the length of the number should be same.
Yes. Okay. So let's assume that the length of the number is same in both the cases. In that case, what happens?
Also, so slides have to typos.
Correct.
Your slides have two typos.
Slides
You're
have two
outputting
typos.
y.
There are many typos actually.
Well, they're outputting y regardless, both the times.
They're outputting y regardless.
So output y if x sub y is less than y sub I, else
Oh,
output
okay.
y.
Yes.
Yeah.
Oh, right.
Else
It
output
should,
X.
it should be else, output x. Right. Right. Very good point. Yeah, there will be output x. Yeah. So, but assuming that this one was there was no typo, which would have been the correct algorithm?
First one.
First one. Which is the better algorithm?
Second one would be faster, assuming that the digit where difference occurs is not beyond the 5th digit.
Right. So see here, there is something here. The second one is faster. First one is more correct. Now, what happened to the second one? Is that correct? I mean, it is wrong sometimes, but when is it wrong? It is wrong if the difference is after the fifth digit.
Yeah.
Or in other words, if the x and y differ in a very small fraction, I mean, if y is significantly lower than x or x is significantly lower than y, I would give the correct answer. But if not, yeah, the algorithm might make some mistake. But this is a faster algorithm. Within just constant number of checks, I can output the correct answer. This is not the case. So in real life, which one would you apply?
Sir, algorithm 2.
Algorithm 2?
It would depend on the use case. Really.
First one. I mean, the first one always
If
kind
we
of
know
give,
that- If we know that the difference between the values we're trying to compare is within the order of magnitude 10 to the 5, then we can apply the second one. And if it is anything smaller than that, then we have to apply the first
Right.
Or even if we can ignore small differences in some cases.
Yes.
So in real world, there might be cases that where small differences might not matter. So in that
No,
case, we
exactly.
can also use.
Exactly. That will be the one where difference is in order of 10 to the 5, not
Right.
less than that.
So you guys are completely right. There's no correct answer to this question that I asked. It depends upon the need of the hour. Okay. For example, I will tell you, like, how many times have you picked up a book and your friend has a similar book of a different edition, and you want to check whether these two books are same or different? Have you ever faced this problem? Or
Yes,
is it a
sir.
very old school problem? Nowadays, you don't use books.
No, like even in ebooks, there are edition related issues, right? So
Even in ebook, there are edition related. How do you check it? How do you check it whether they are actually significantly different or are the same?
First, we check the content.
Look at the
First you check the
content.
content, yes.
Sample random pages. And see
Sample
if, like,
random
there's a-
pages.
see if there is a difference at some place.
Sir,
that
see the
the-
cover page. In most of the case, it is written which edition it is.
No, let's say editions are too different. That you know. But you are not interested in the editions whether they are different or not. They are more interested whether whether there's major changes in the content, right?
The content and the preface would give the right answer.
Will it always give the right answer? What happens
Yes,
there were
sir,
some
in the
typos which
preface-
has
So
been
the
fixed?
now number of pages might be different.
Oh, what happens if there's some typos that has been fixed?
Sir, the typos would not change the context of the preface, I think.
Errata, sir.
Because
You
the
can check
writer
errata.
always mentions whatever changes are present in this edition than the previous edition.
Sir, if we check thoroughly, we have to check the full book. But if we do not want to check thoroughly, then we can sample the random pages.
Right.
The preface would be always better because in the preface, the writer always mentions the summary of the book, whatever changes he has done from the previous editions, and whatever.
Good. So
changes he-
yes, you are right. So there might be such kind of things in which there are prefaces where they have mentioned it very carefully. Okay. But many times there might not be, there might be saying that, okay, I made some small changes. Where the small changes, you have no idea. Or maybe you don't know whether they have told small changes just to sell the book second time. So
Yes,
in
sir.
that situation, you do take some actions like the algorithm too. When you randomly check some pages, you randomly take you look at the content, whether the contents are more or less fine. So you are looking at only a small fraction of the thing and trying to understand whether these two things are same. But again, if you have to do it very correctly, answer this very perfectly, in that case, you have to do it slowly, right? By algorithm one. So it depends upon, so it all depends upon how much, I mean, what is the need of this? Okay. So again, I can skip all of that. Now let's go back to another problem. So this is a very simple problem that is there. So you remember how to do this GCD of these two numbers? What is GCD?
Highest common factor.
Highest
Greatest
common,
largest-
also called the HCF.
Largest number which divides
The
both of the
smallest
numbers.
number which is divisible by.
That's the LCM.
That's the
This is
LCM.
largest number which divides the both the numbers.
Yes, it's called greatest common divisor or highest common factor, HCF, in some sense. So how do you find it? A standard way or simple way is just to keep on seeing whether y divides a and b. And if y divides out a and b, you will output y. And you keep on increasing. You'll, okay, fine, y divides a and b. Now, can something else output a and b? Is there a bigger thing that outputs a and b? Right? So I keep on incrementing it. Okay. Oh, here also there is a mistake. I think this should be output x.
yes,
This will also be output X. Right. So this is a GCD. But do you guys remember how you used to calculate GCD in school?
Yes, sir. Taking differences because GCD of AB and A minus B remains the same.
Yes. So you used to do something like this. You used to take a GCD of AB, you used to divide B or by A. So in this case, Y by X. You write Y to be equals to some QX plus R. Whatever that R is, okay, you now take this thing that you have divided by, you make that one Y and this remainder as X, and you repeat the whole process. And you keep on dividing it as long as R is not 0, right? And as soon as R is
0 or
0,
1 or 1, right?
Okay, I mean, you should output this X when you are done, basically.
Right.
Right? At 1, you will do it one more step and you get 0 remainder, right?
So, but at 1 we can always stop, right? Because, well, fine, yeah, true.
I mean, you might not get 1, you might get a 0 before 1.
Yeah, that's the case.
Now, this is something that you did in your class 2. But now again, if you guys have forgotten, then please revise it. I don't know how will you find a class 2 book, but revise it. How do you do it? GCD of A and B. And now the question is that, of course, the first question is that you guys have done it continuously in your life. And the first thing is this algorithm correct? So does it always output the correct answer? Or it does sometimes output the correct answer? And the next important thing is how many steps does this algorithm need? Okay, can you tell me how many steps does this algorithm need? How many
Yes.
steps does algorithm 5 needs?
Yes,
Needs A step.
Huh?
Number of steps is A until at the worst case.
So again, so what about other people? What are the other people say? How many things does it need? Nobody has
First
any
one
idea?
need order n and second one will
Yeah.
need log n.
worst case would be A, the minimum of A and B.
Okay, so already you guys have used a adjective, worst case.
Yeah.
So it is not very clear. Why should you consider worst case? What is worst
In this
case?
case, it should always run up till A, right? There's no need for worst case. In any case, it should run till A because there's no other terminating
Very good.
condition in the loop.
That's true. So this particular algorithm, as it is written, will always have this number of times the while loop will run is a number of times, right?
Right. Okay.
And
Yes.
inside them there are some constant number of steps that you do. So the total runtime of this algorithm is order A. Always. What about this? Now this one is a bit more trickier. First of all, if A divides B, then this can take just one step. Right?
Yes, sir.
And otherwise, how much time does it take?
Sir, it also takes the A minimum of A and B steps.
It always also takes minimum of A or B steps?
Sir,
Not
log
always,
n.
worst case.
In worst case?
So log n.
Somebody saying log n. What is
In
length?
worst case, it takes A or B, sir.
Is worst case takes A or B?
Yes, sir.
Why?
Sir, because I have seen an example where
Oh,
Euclidean
no. Don't use a seeing an example. Okay, that's exactly where this thing goes completely wrong.
No, sir. When Euclidean was run on Fibonacci sequence,
Yes.
and like every time we run on say fn minus 1 and fn, we just go one sequence behind. So
Right.
in
So-
that case, it will take
So
the
how much time
maximum-
does it take? Let's see whether you have
minimum-
understood what you have seen.
so it will.
How much time does it take? So you are saying that if A is equals to Fn minus 1 and B equals to Fn, how much time will it take?
So it will take n steps.
Oh, excellent. But what is A here?
Okay, A is the okay. Then it will take log n
So,
steps.
okay, yeah, because Fibonacci is an exponential sequence, so it will take long.
Okay, so
Log
see,
n
you
sequence.
see that how much you, because you memorize this whole thing, that's what happened. There's not A steps. Okay. Now I leave it to you guys. I think this proof is there in this lecture only, but I am not going to do it.
Sir, another thing here, assuming A is less than B, right? That part is really necessary.
No, I'm not assuming A is less than B.
So, but then
Think about it.
how are you dividing? Okay.
Well, you'll have Q equals to 0, and then it will flip.
Ah, I see. Okay. But won't it fail?
Think about it.
Okay, sir.
Okay. So this is exactly where these are the same. These are the questions that you should have asked when you were class 2. Okay. What is HCF of when you are doing this HCF of 48 and 20? Where you taught that okay, first think out which is the larger one and then start with that. Or was it just, or even if it was told, why was it told?
If we took the smaller one to, then after another step, that automatically the larger number will come.
Yes, that's what should come.
So we are basically reducing one step. It is
Exactly.
the algorithm is becoming faster.
We will be reducing one step. That's true. But also you need one step to find out which one is larger.
So basically, there is not much difference.
Yeah.
Same, both the things.
So I leave you guys to think about this set of questions. Okay. So how many steps does the algorithm need? Okay. So there are two things that you should always think of for any algorithm. Doesn't matter for GCD or whatsoever. First of all, is the algorithm correct? Is it always correct? Is it sometimes correct? Is it maybe correct? This is what is called the correctness of an algorithm. Okay. At least in the beginning of the course, we will spend some amount of time to prove the correctness of an algorithm. Now, the next thing is that how many steps are required by the algorithm? Now, there are not very well-defined concepts. I mean, there are well-defined concepts, but there are no canonical answer to it. Number of them is that what is the maximum number of steps taken by this algorithm? In other words, in the worst setting, what is the number of steps required? Okay. Also, what is the worst input for this algorithm? What is the average number of steps required? What does average mean? Now, the average can mean a lot of things. Maybe A and B are drawn randomly from 1 to n. Then what happens? Okay. Maybe the algorithm itself has some randomness in it. So these are the kind of questions that you are expected to ask for any of these algorithms. So I'm not going to talk about it. Okay, so I'm not going into details into Euclid's algorithm. You can go and check the video or the slides and you figure out how many number of times does the Euclid algorithm need, and how do you prove that? This is important. Okay, so coming back to the question of what is an algorithm, it is a step-by-step process of doing a particular task, and the goal. Now, this is where things are important. Okay, you want to minimize the amount of resources needed by the algorithm. Now, the amount of resources can mean a lot of things. Most of the time, at least in this course, we will be talking mostly about the amount of time, or what we call as the time complexity or runtime. And there are different ways of calculating it. The worst case runtime, the average case runtime, or the expected runtime. There are also things like called the amortized runtime, which I'm not going into that details that much. But then there are other things like space. How much space is required? Okay. I mean, there are algorithms where literally the space in your computer will matter a lot. How much space is actually taken? There are other things about how much of randomness, how much of communication, amount of samples. There are lots and lots of different resources under which a particular algorithm is tested. In this first course of algorithms, we will be going only into number of steps. I mean, the worst case runtime, a little bit of average case runtime, and maybe just 1 or 2 lectures on space complexity, the amount of space. Rest of them, we will not be going into it that much. I might give you some intuition or high level motivation for some of the problems, but those will not be covered in this first course. The other thing is that we want to maximize the amount of correctness in an algorithm. So can we say that the algorithm is correct in worst case? Can we say it is approximately correct? It's almost correct. Can you say it is mostly correct? So there, all of these questions come up in the picture. And this is the basic idea of algorithm. So throughout this course and throughout anything that you do in your computer science, MTech or JRF from now on, every possible things should be looked in these two angles: how to minimize the resources and how to maximize the correctness. Okay. Now, when we are talking about time complexity or space complexity or something like that, what do I mean by that? Does it mean that if I run it on this computer, it takes this much second? Or if I run it on a Mac machine of this configuration, then it has taken 15 nanoseconds. Yes, that is one form of compute calculation that you can think of. Okay, it is done. Particularly in the world of machine learning and all, some of it is done in that way. Okay, but for most of the cases, at least for the purpose of this course and for the purpose of most of the other things that you do in your computer science world, usually we want to understand these things of runtime or time complexity, space complexity, and so on, in terms of the size of the input. Okay, so the main idea is that this is an algorithm. An algorithm is there irrespective of the machine. An algorithm is there irrespective of the of a particular setup being there. As you can see, that algorithm is there from the Euclid's time, or from you had done it from your when you first learned to add two numbers, right? So algorithm is independent of computers. Therefore, it is not about which computer under which you are running it. It is about the number of steps. Number of steps with respect to what? with respect to input size. So that is kind of an important thing. So input size is the number of bits required to specify the input. So for example, in this Euclid's algorithm, what is the input size? Can somebody say what is the input size?
A and B.
A and B are inputs. What is the size of the input?
Order 1.
Order 1. Okay, why is it order 1?
Size would be integer size.
So basically, the space is constant, right? There are two numbers basically.
There are two numbers. Okay, so you are saying that if there are two numbers, they are constant.
So it's
Yes,
a log of A, comma log of B and max of these, because we need to represent A and B in terms of bits.
Right. So think of this one as this thing. So this is something, GCD of AB is something that you don't just solve, you don't apply this algorithm to find 48 and 20, right? You want to apply this algorithm to find out the GCD of two numbers. Both of them can be, say, 2000 digits long. For people coming from this world of programming and all, can you write a 2000 digit number? How will you store a 2000 digit number?
Strings.
As a string.
Yeah.
As a string meaning?
I mean, take the numbers as a string, like 1, 2, 3, 4 at 2000 length string.
Achha. So you have already a 2000 length string. So is the size constant or 2000?
No, I mean, depending on the number of digits, the size may vary.
Exactly. Right?
Yes, sir.
So the size of the inputs is the number of digits. Because you have to store that number. It is not order 1. Okay. Now, in the world of computers, you want to store it as number of bits. So it will be order. It would be order
Log n.
log n base 2.
Yeah.
2.
Yeah.
If you write it in as digits, it would be log n base
2.
no.
Oh,
If you
I
write it
mean,
in terms of digits, it would be log n base 10.
10.
10, sorry.
Okay. Now log n base 10 and log n base 2 are
Like
constant within constant of each other. It is
Yes,
order
different by
of log n.
Yeah.
Okay. So in that sense, whether this is given, whether E and B are given as integers or as bits, as digits or as bits, the number of the space required to represent A is order log A. Number of space required to represent B is order log B. Okay. So the input size is order log A plus log B. Is this clear? This is something very crucial. These are not 2 digits. It has 2 digits, but think of them as not just 2 small digits. They can be massive digits, massive numbers. Now you might say that, oh no, but we will in modern day computers, everything is done in respect to cube in the bits. So every maybe 8 digits is represented as a bit. So byte. So anything less than 2 to the power 8 can be written as a byte. Yes, you're right. But what happens if I have a 2000 digit number? how many bytes you will need. Okay. So the input is always therefore measured in terms of the number of bits or amount of time required to amount of space required to give the two inputs. Now give the inputs. Is this problem clear? Okay.
Yes, sir, it is.
Yes, sir.
Yes.
Sir, you're saying input for the GCD algorithm or input for any general algorithm is measured in the storage bits required?
Input for any algorithm
Okay.
is measured in the number of bits required to store the object. Okay.
Okay.
That is, I mean, the bigger the input, harder it is. That's the main idea. Okay.
Okay.
Now this is something very crucial.
Sir, like I know a bit about.
Sorry.
Hello, sir.
Yeah, tell me.
Can I speak?
Yeah. Go ahead.
So, say we, I know a bit about binary search, which takes order of log n, where n is the number of inputs given.
N is the number
Okay.
of
Okay.
inputs.
Okay, sir. Fine. Understood.
Okay.
Understood.
Okay. Fine. Okay. So
Yes, sir.
Yeah. So the input size is the size of the number of bits required to specify the input. Okay. Sometimes we might use some other measures, but that will come later on. I will explain them as it when it comes. And the time complexity or space complexity is measured as a function of the input size. Okay. Now, how to check the correctness of an algorithm? How do you check whether an algorithm is correct? Now, this is a very important thing. How many of you are coming from with a little bit knowledge of machine learning, data science, whatever? Nobody has any knowledge of machine learning or data science?
Yes, sir.
Oh, so you are the only person who have heard of machine learning, is it?
No, sir, only basic. We have heard of machine learning, but not particularly.
Yeah, I was hoping that to get some answers. People
Sir, I have did a basic course in machine learning also.
Yeah. Okay. So, okay, how do you check whether an algorithm is correct in machine learning?
You measure the performance. You measure its performance using a test data set.
Using a test data set, using what is called a benchmark. Right? So this is an important way of testing correctness of an algorithm. This is called what we call as empirical methods. You run the algorithm on a set of benchmarks, then you check whether the algorithm is outputting correct on those benchmarks. And if they are, then you say that, oh, this algorithm has this performance. Now, this is something that is easy to check, right? I mean, it's easy to check, meaning, I guess I'm not saying that it is easy to write a program and all, but it is still doable, right? You have a benchmark, you run it, you have a big machine running in some GPU and all, you upload things there and run it, and that's it. Now, there is a problem with this thing. What is the problem? You have verified whether the algorithm is correct on some set of inputs. You have not checked whether the algorithm is correct in all set of inputs. Now, this you have seen in many places, like you have seen that even now the self-driving cars algorithms fail, or the machine, or there are some Boeing crashes that happen because of their problem with their algorithms. What was the problem with their algorithms?
The
issue is-
benchmark wasn't exhaustive.
The benchmark was not exhaustive, right? So some part of the data, I mean, some input was not tested upon, or some class of inputs were not tested upon. And that is a problem with empirical test, always. So empirical testing has this major problem. The correctness depends upon how good the benchmarks are, and you are never going to be certain about how good the benchmarks are. But also at the same time, these algorithms are so complicated that they're very hard to do anything other than that. Now, there is another way of checking correctness. So this one was what was used before the start of the modern data science kind of work. This is what is called a mathematically rigorous proof. So here you take an algorithm, you try to understand what the algorithm is doing, you try to argue, and you give a mathematically rigorous argument about why the algorithm is correct. Now, the good thing is that this algorithm is almost, this algorithm, if it passes this test, will always be correct. But it would be much harder to prove that correctness. It is not like choosing a benchmark and running. So both these techniques have their pros and cons. In fact, sometimes in maybe third, fourth week of my course, I will be talking about a very well-known machine learning algorithm called perceptron learning algorithm. It started with the empirical method. It was kind of the first machine learning language that you can think of. It was started by the biologist, and in fact, that is the exact reason why you have names like neural networks and all those things in computer science now, because it was started from the biology community. And they had a empirical correct proof, and it took 20 years and some beautiful math to finally prove the mathematically correctness of that algorithm. It's called perceptron learning algorithm. If you guys are interested, you can go and check it out in the Wikipedia. I will also be covering it some time to time. But then there are also other algorithms for which we are far from it. I personally work on an area called SAT solvers, something that I will again talk about it later on. An extremely complicated problem, which we don't believe can have a mathematically correct proof, but somehow we have lots of empirical results that says that it's correct. So we are always stuck with this two kind of things. Many of you who will be going on to do research in machine learning and those areas and in industry will be following this empirical methods. But you should always remember that these areas have a problem, whereas the mathematically rigorous proofs are much harder to be proved, but they're correct. So there are these two extreme cases. So in this course, we will be mostly focusing on the second, okay? And this is where I think this is the special. Somebody asked me last time that whether this course will be only theory and all. The reason that this course is more theoretical is because a big chunk of this course is about proving correctness of basic problems, basic algorithms. So we will not be going deep into various algorithmic concepts. We will be doing some very basic algorithmic concepts, things that are kind of the building block for all other algorithms that are done nowadays. I will of course give you pointers to various things as we go on. But our focus for this whole course will be on simple algorithms, simple small algorithms for which we will be giving mathematically correct proofs. Okay, so the goal and design of this course will be, okay, or in general, in analysis, design analysis of algorithms, the design an algorithm. So this design part is a very important thing. Prove the correctness of the algorithm. Then you want to calculate the amount of resources needed by this algorithm. There are various different kind of resources that we can talk about. And then you try to design an improved algorithm. An algorithm which possibly takes less resources or has some other qualities. And also we can sometimes talk about running on the benchmark to evaluate the algorithms empirically. And finally, now a last part that is there, and this is something that we'll be doing in this course just a little bit, is that sometimes it's important for us to understand this whole measure of designing, calculating, and improving the algorithm. How long can it go on? Can I always keep on improving the algorithms? So as time goes on, and if a more intelligent person comes in, will a more faster algorithm be designed? Or is there some inherent bottleneck to obtaining a better algorithm? So this is what we call as the lower bound. To understanding that it is not possible to improve an algorithm beyond this point. Now this thing we will be doing in little bit in the beginning of the course, and later on in the course when we will be talking about things like NP completeness and so on, we will be going into this lower bounds thing.
Sir, how do you decide that something is best possible?
Yeah, exactly. How can we show that something is not possible, right?
Yes, sir, exactly. Like you might have missed it.
Sorry?
You might have missed one like better algorithm or something.
You might have missed
How do
one
you know
better
that?
algorithm, right? Good. So that's why you don't prove that, okay, so these are the best algorithms. You come up with a complete different proof, kind of saying that, see, any algorithm that solves this problem must have this property. You first prove it. And then you show that, okay, an algorithm that has this properties will have to take this much amount of time. Or this
We
much
find the
amount of
bare
time.
minimum required to solve the problem.
Kind of, you can think of.
I see.
Okay. Now this, of course, I will go into at least one lower bound in good depth very soon in the next 2 weeks or so. But I should also point out that obtaining lower bound is one of the hardest problems in whole of computer science. Okay. So our understanding of this lower bound is quite low. But this is basically how overall a concept of algorithms progress. You start designing an algorithm, you prove the correctness, then you calculate the amount of resources required. Okay, good. That gives us first algorithm. The next algorithm, try to design an improved algorithm, and so on. And you keep on doing it. And then when it comes down to deployment of the algorithm in the real life issues, you run it on benchmark data, evaluate the algorithm empirically, and so on. Okay, so I think this should be the end of the introduction of this, what will be done in this algorithms course. Now, this is something that's very crucial, because without having a good understanding of this, what is an algorithms and what is required of an algorithm's code, particularly the concept of correctness of proof of correctness, we cannot progress further. So is this clear? Any doubts, any questions? By the way, I can also tell you another thing, that I would really encourage you guys to ask me questions, unmute yourselves, shout out, ask questions. Don't worry about how stupid or simple silly these questions can be. I will not be unhappy or sad at all if you ask me questions. I'll be very happy. Okay, so you guys, none of you have any questions, or maybe all of you are going to sleep. Most likely latter. So, okay, so with this, I think, so in the next class, I will start with the algorithm, the sorting algorithms. But before we start the sorting algorithms, a very important thing is the searching. When you are given a collection of objects and you want to search whether this objects, whether a particular object is there in that set of objects that has been given to you. Okay, so this is exactly the problem that we would like to start with. Now, I am not going to cover that algorithm in class. That algorithm is there in the web page. A video is there, the slides are there, and also there is another video and slide about how to prove correctness of the algorithm that are discussed there.
Sir, in the videos, the video is on binary search, right? Not
Yes.
sorting.
Yes, it's searching in a sorted array.
Yeah, okay. So sorting is covered in that video. Okay.
No, sorting is not covered. You are assume that it is sorted, and then how to sort it, we will come later on.
Okay, sir. Okay, sir. I got confused.
Okay.
So
So
can
if-
you talk
yeah.
about why you mentioned randomness and resources?
Sorry?
Like you said, like one of the resources required, the slide reads,
Yes.
is randomness.
Yes.
Can you talk about what you mean by that?
So many algorithms are there that are randomized. Okay. So by randomized, I mean that the algorithm will toss some coins and decide whether to do this or do that.
To improve their average behavior.
To improve their behavior.
I see.
Okay.
Another question related to that. Another question related to that.
Yeah.
When you were initially discussing the algorithms in the initial few slides,
Yeah.
when you were discussing the average complexity,
Right.
you mentioned that there can be several types of complex average, sense of average, in that average over the input range and average due to the randomization of the algorithms. But those are the two cases. Like, can you give some other examples? Because in my mind, in some sense, average means the expectation time. So what
Okay, so
can
average is the expectation. You're completely right. Okay. By mostly average do mean the expectation, but expectation also has another meaning, right? From the randomized point of view. Okay. So
yes, yes.
In the general, the algorithm. Okay. So first of all, what is average and what is expectation? How is average related to expectation? Can you tell?
So in
Why?
average scenario, we have some deterministic values on which we calculate an average.
Right.
Expectation is the, like, in some sense, the average over a stochastic stream of variables or data that we get, and some probability measure associated with those data.
Exactly.
So we
What are the
can
probability measure? What is the probability measure?
what do you mean by that? Like, can you
So
elaborate on that?
the weights in our weighted average in case of expectation is just the probability of the certain event occurring. That's it. In case of
Right.
normal average, it's just the mean. It's just the one, as we don't really have.
Normal
a
average
randomness.
is the expectation over the uniform distribution.
Yes, yes.
Yes, 1 by n, exactly.
But now we can talk about other distributions.
Okay, so that okay.
So there are two kind of, hold on, just 1 second. There are two kind of randomness that can comes here. Okay. Number one is that, as somebody pointed out, the algorithm might have a randomness in itself. The algorithm might use randomness by itself. Okay, so given an input, the algorithm might toss some coins, might take some random bits and decide to do this or do that. Okay, so that is a randomness within a algorithm. But also we can ask what happens if the inputs are drawn randomly. Okay, and that would be the average thing that you are talking about.
Sir, when you mention randomness as a resource, do you mean the cost of creating true randomness? Like
that is
true
also
random
there. That is also studied.
Yeah, I see.
That is also studied. Cost of creating true randomness. Whether do you need pure randomness? Do you need pairwise
Pseudo.
randomness? All of these things are studied. Okay. Not in this course, but they are studied. Yeah, seriously studied. Also, the amount of random points. How many random bits do you need? That also is studied. Yeah. So in this course, again, very soon we will see a randomized algorithm, but that will be just a yeah, that will be just a start in some sense. Okay, but more complicated randomized algorithms will.
Sir, I had a logistic question as well. May I ask?
Yeah.
So I'm expecting, like in upcoming assignments, you would be expecting pseudocodes as solutions, right?
Right.
So in place of that, because I'm planning to do all of it in LaTeX, is it okay if I submit Python codes instead of like writing pseudocode, because I'll have to do it twice? I'm also going to implement in Python. So is that okay?
I mean, that's fine.
Okay.
Okay. Yeah. But yeah, that's fine. That's not a big deal. Yeah. So if you are planning to implement all of them, that's, I mean, that's fine. Great.
Sir?
Yeah.
Regarding the marking, like, is the marking a bit lenient, or is it like if we, for a proof or something, if we give the general idea and make some small mistakes in the mathematics or something like that, will we be heavily penalized?
Don't worry about all these markings and all at this point. Okay. As I told you that I mean, most likely none of these things. I mean, see, again, if you are trying to write a proof, okay, all I see is whether you have got the main idea of the proof or not. Okay. If you have got the main idea of the proof, that's perfectly fine with me.
Okay.
So but don't worry about this of marks and all. You can ask. I mean, I'm not saying that I'm a lenient person, but I'll not be trying to, torture you guys with such trivialities.
So, sir, another logistical question rather related to this. As this course is online, can you just like include feedback in for assignments and such in comment in the PDF? Because otherwise it's hard to review for
sir.
us. So that is an issue we faced in the last semester when we did not receive assignments or did not receive proper reviews and did not know how to correct them.
Yeah, sir, this was the problem with rigor as well. We didn't know.
Okay, so there are two things that I can say.
Reference would suffice.
So there are two things. Of course, we will be putting, we will be at least in the initial parts possibly putting up some what to say, kind of solutions. Okay, model solutions. One thing. Number two, the TAs will be correcting in the class, in the Google Classroom, which means that they will be putting in comments inside that, inside the Google Classroom. There is a provision of putting comments. Okay. And thirdly is that although I am teaching online, many of the other things are offline, right? Including TAs, tutorials.
Yes.
So if you have any doubts about how they have corrected or not corrected and so on, feel free to go and just ask them. Or you will actually see them in the tutorial sessions. Okay. Many times, instead of we just writing that, okay, I have deducted 1 mark for this, it might be something important to kind of have a chat with the TAs so that you can understand what are they trying to say exactly. Okay. So the assignments will be assignment, there will be 5 assignments or something like that. And usually my experience says that everybody will be doing 100% almost in the assignments and all. Okay. Also, I would be taking only the best 4 or something like that, best 3 and so on and so forth of that. So don't worry about the assignments, how much marks you are getting. I mean, even if you get 1 mark less or more, that doesn't matter. It is more important to use the assignment to understand whether you are understanding things, if you are writing things correctly or not, and so on and so forth. Okay. Again, as I told you, I will be very happy if you guys discuss your assignments with your other friends. Okay, I'm not asking you not to discuss your assignments with other friends. But at the end of the day, you have to write it yourself. You have to write it yourself, understand it, what this whole thing's about, and then write it. And see whether you, yeah. So if you have any doubts about the assignments, ask the TAs, get clarification. So this will help you in understanding various things about this course. Okay, any other things? Any other comments? Okay, I can see that there are some 5 or 6 of you are actually answering these various things, and the rest of you are just not answering. Now, it is true that I have told that I will not take any attendance in the class, but that doesn't mean that you guys can just come here and not respond at all. I might just call out names and try to ask you guys certain things. I mean, this is not the first time you're doing an online class, and I guess you guys are very aware of the fact that if you don't respond at all, neither am I seeing your faces, nor I am seeing your voice, hearing your voices, it is very hard for me to understand what's going on. So another thing is that if you guys have, if the background is not too noisy, can you guys please keep yourself unmuted?
Now, sir.
Now or even otherwise, even for the next class or something, always, in fact.
So it will get too noisy though.
If you think that your background is too noisy, then it's fine. You don't have to keep yourself unmuted always.
No, sir. Just because nearly 50 people are involved, even if some noise is there in some room, it will all get added up and it will become too noisy.
Okay.
Yes, sir. And some of us are doing classes together, so the voice of class will also echo in that way.
Okay. So you all are kind of, none of you are in the classroom, is it? Is anybody of you in the classroom?
Some of us, sir.
In the same classroom?
In 520.
In 520?
Yes, sir.
And you are
Yes, sir.
still logged in individually.
Yes, sir.
Yes, sir.
Okay. So the projection is not working.
Projector is working.
Hmm?
It is working, sir.
We haven't started it.
Oh, you have not started. Okay. 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 So I think I will stop today right now. In the next class, I'll start with sorting. But as a homework, please go over these 3 videos that has been posted. One of them I went over it today only. Right now, the binary, this searching binary search video and the proof video. Please go over it. Okay, I will assume that you will be seeing them and you will starting from that. Okay, so see you on Tuesday, sorry, on Wednesday, and on Tuesday the MTech CRS people have their first tutorial at 4:30, right? I will send a mail confirming the classroom.
Thank you, sir.
Okay.